In this video, we will apply the absolute positioning principle by using pseudo-range measurements. So for this purpose, we will use a station's first epoch. So this is the file which you have in your repository in this week. So I copied the measurements here for the first epoch. So the 12 measurements for the GPS satellites, and passed these observations to my file. So as you can see, the first number is ending with decimal 690, and the last one 402. So you can easily see 690 and 402. So I kept the sequence of the satellites, the sequence of the measurements in its original form. So I did not change anything. And the satellites was observed at the point at this time. So this time is the receiver's clock time. So this time refers to this receiver's clock, not to the satellite clock. So that's why we obtained the satellite coordinates. So by taking the distance between the satellite and the point into account, so because these satellites send their signals, and nearly 70 milliseconds or 78 milliseconds later, the satellite arrives at the location. So and at that point, the satellite moves forward. So this fact must also be taken into account for the satellite's position. So I have computed the satellite's position. So you see in the same order, beginning with 5, so ending with 31 in the same order. So the satellites X, Y, and Z coordinates in Earth-centered, Earth-fixed coordinates, and the satellite's clock error is also included. As you can see, this clock errors range between milliseconds, so nearly milliseconds, to the nearly to the nanoseconds level. Okay, so we have now the observations, 12 observations, and 12 satellite coordinates. I also obtained the approximate coordinate of my position from the observation file. So I copied these coordinates as a row vector. Now, let's apply our absolute positioning principle, which has been introduced in a previous video. So let's try to compute the receiver's position by using least squares estimation method. So before proceeding, let's try to plot the so-called azimuth elevation diagram, or azimuth elevation plot, or the sky plot for the distribution of the satellites in the sky. So first, let's try to find the length of our observation. So we have 12 observations, and if we obtain the length, so we can make some for loops, so for some for iteration. That's why we need the length of the number of observations. So now for I is equal to 1 to n, now I would like to determine the azimuth elevation angle for each of the satellites. So the satellite's coordinates are given here. By using these coordinates, I want to compute the satellite's azimuth and elevation from my point, so whose approximate positions are given. So the approximate position must not be within a millimeter accuracy. So this may be within 1 kilometer accuracy, so this, it will change nothing because I'm only plotting the sky view for the sky plot of the satellites in a projection, in an azimuthal projection. So I will make no further calculations for the moment. Now let's apply the azimuth. So I want to get the azimuth of the satellites for the ith satellite. So the elevation of the ith satellite. So I is equal to 1. So this means that I will loop over the sat core here. The first item will be the 5th satellite, the number 5, the satellite with having number 5, and the coordinates will be acquired from this sat core matrix or vector. So then some computations will be carried out there. So the slant distance between my receiver and the satellite, slant distance I. So now I created previously a function. So a function xyz to lowercase x, y, z, and for this purpose I need x, y, z approximate coordinates and sat coordinates for the ith observation. So be aware, I will use the x, y, z coordinates so that the first item, the first column will correspond to the satellite number, and the second, third, and fourth columns will refer to the satellite's coordinates. That's why I'm writing 2 up to 4 now. So this function, what about this function? So creating a function, why do I need to create a function? Because I will carry out finding the azimuth and elevation 12 times. So in order to avoid every time, by copying and pasting to my function, which computes from the Cartesian coordinates, the local coordinates. So in order to avoid that routine working, so I created a function, and the function looks like this here. So now I'm changing to the function here. So this code is already available. We have made previously in our videos, in our lectures on Octave platform. So I only changed in compact form. I omitted some explanations and etc. So this is the same here which we have applied previously. So you see again a function is available because for the computation of the azimuth elevation and slant values, I also need my standing points coordinates in Earth-centered, Earth-fixed coordinates, so the Cartesian coordinates. So for that reason, I need to make a conversion from the Cartesian to the ellipsoidal surface coordinates. So the ellipsoidal coordinates will be obtained by changing my approximate coordinates to the ellipsoidal surface coordinates. And then this is realized again by using a function, and by using this function. And this is already available, and I changed this to my previous code, which I have generated during the lecture, to a function. So as you see, generating a function, you are already familiar with the computer programming lecture, so it is I will give no further details, so you can easily see how to convert to a function. So as you see here, I should provide at the right hand side the coordinates in the Cartesian coordinates given here x, y, z, for example, for my position, and at the end of this function realization, I will get my ellipsoidal surface coordinates, so ellipsoidal latitude, longitude, and height value. So this code is also available. So as you can see, a function must begin with the function command here and end again with end function. So this is the point where you should be mostly aware. So it is easy, as you can see. So after this BL and H are computed, you can now create the rotation matrix. So the rotation matrix from the Cartesian system to the local system. So, and this is realized by using the value. So azimuth, elevation, and slant distances are computed, and these again will be brought back to the function where I am requesting. So as you see, azimuth, elevation, and slant, the values will be obtained from the function. Now let's proceed again. So we would like to make a plot. So for this, I am writing so as a handle. It is anything. So I'm writing handle. So I'm going to produce a polar plot. So because the polar plot, you can see on the Earth's surface how the satellites in the sky are distributed. So I will use for this azimuth I. So the azimuth elevation angles are provided in degree units, but the polar function requests us to give the azimuth angle in radian units. That's why I need to convert to radian. So now elevation angle must also be provided, but the polar plot uses the elevation angle from the direction of zenith, not from the horizon. That's why I must subtract 90 from my elevation angle. So and I will plot the satellites by using this sign asterisk with red color, for example. So now again, I must make some arrangement so that I can get the plot in a routine way. So this is the x direction of the plot should be in reverse order, because it uses, if I plot in this way without making any arrangement here in the x direction, I will get in the the angle measurement in the not in clockwise direction, in the counter clockwise direction. So this is in mathematical way. That's why I need to bring to to the normal. So y direction should be the normal. So I'm setting again this. Sorry. Okay. Now uh, uh, I must view this plot. So you can skip these formalities, because so the viewing is looking from a certain direction, so that you see in a local coordinate system. So, and at the end I will hold on, I will plot for each of the satellite, and I will hold that on. Now I'm saving and running it. So we will now see the satellites. So the grids, there are two. You see 50 and 100. It is not so good. So let's increase the gridding. The grid intervals should be smaller. So for that purpose, let's write down. So here set a GCA. So Arctic. So R means so the azimuthal, so the polar coordinates. So as you know, in mathematics, polar coordinates in a plane are given by two parameters, theta and r distance. So the Arctic means the elevation, okay, angle interval. So now, so we will write this. So the beginning from 0 increases with 15 up to 90. Now let's again, so you see now better every 15 degrees interval. So this satellite, so my point is here at the center, and now there you put a plane. So the plane's zero direction shows the north direction, as you can see. So I see my direction in the clockwise direction. The angles increases in the clockwise direction, and as you can see, the angles 15, 30. So these are the normally zenith angles, okay, but here so it denotes, so it is zenith angles, but the system uses for plotting the zenith angles itself. So this means this point's zenith angle is 90 degree, okay, but its elevation angle, as you can see, it is 0 degrees. So that's why I made some arrangements so that we can get a good view of the satellite position. So let's now have a look to the azimuth and elevation of the satellite. So for this purpose, let's write down the sat core, for example, and azimuth and elevation angle. So let's see. Sorry, what about the problem? Azimuth sat core, and this is my first one. Is the azimuth should be the transpose, elevation should be transpose. As you see here, okay, there's a fifth satellite is in the azimuth of 38 nearly and 9 degrees, okay, elevation angle. So the 9 and the 38, so here, and 9 degree elevation angle. So you see it is here, so 90, and it is so 80 degrees, 75 and 80 degrees. And as you can see, another example, so here the satellite having the highest elevation value is 21. It is minus 38, so means it is nearly 320 degrees, and at zenith angle around 70, so elevation angle around, okay, 78, so which corresponds here, so nearly 12 degrees. So you see it is the closest distance 12 degrees. So this satellite is, as you can see here, so 12 satellites are distributed across the sky in this way. So now let's proceed. We will come to this figure later. And let's now proceed to our, okay, positioning code. For each of the satellite, okay, for each of the satellite, again from I beginning 1 to n, so I can use I again in computer programming here because I have used I up to n here, but this is, okay, n is okay, is used up to the end. That's why I can also be introduced as a new variable, so not a problem. So now first I need to compute the difference. So you you recall at the right-hand side of our equation, so the coefficient matrix, A matrix, and the A matrix element will include the satellite minus position differences divided by the approximate distance. So that's why we try to obtain these coefficients. And so sat core, for this purpose I need to take the difference I to 4. So the first satellite, the second, third, and fourth columns will be included because x, y, and z. These columns will denote x, y, and z respectively. So I will take the difference x, y, z 0. So then I obtain the difference. So now I am going to get the first, second, and third column of my coefficients matrix. How will I do that? So I will do that I, comma 1 to 3. So and I will divide dxyz by the norm, norm of my dxyz. So as you recall, so there must be a minus sign in front of the difference. So we must be careful at that location. Now my fourth column will include the satellite clock error. Satellite clock error, as you can recall. So this includes c times dtk. So in this case, I can put c, but I would like to get the multiplication itself. That's why I'm putting simply 1, so that the multiplication, instead of the time in second unit, I will obtain the multiplication of the velocity of light times the time. So this will result in meter units. So I will then obtain the value itself, 1. Now I need the left-hand side. As you recall, the left-hand side should include L, I. So is the difference from my observations, I. So as you see here, P, the first number is the satellite number, and the second number is my row observation. That's why I'm taking the first row, the second column. So minus norm of my my observations. So norm of the distance by using the approximate coordinates now. And here I must also take the satellite clock error into account. For this reason, I'm using the sat core. So for the ith row, this is the 1, 2, 3, 4, 5. This is the fifth element. So the clock error, satellite clock error, will be the fifth element that I'm including here. So now I ended here. I will make the QXX matrix. So this is the multiplication of the of the A transpose times A. So this is the coefficients matrix A, but I will take the inverse. So if you look at the videos in the 8th week, we have made for that. So you can understand. So these are the equations used for the least square solution. Now I'm proceeding. My unknowns will be QXX times A transpose times L. So I'm going to obtain the residuals, and the residuals will be obtained A times unknowns X minus L. Now let's we have the first value, so the first iteration. So let's run it and let's look at the v values and also the x value. So there's an error here. Let's have a look. So we have some, sorry, and that's the reason why we are getting errors. So okay, fourth. So we must be careful because L, as you see here, L is a matrix 1 by 12, so it must be 12 by 1. It must be a vector, but it must be a column vector. So you see here a row vector. That's why I need to take the transpose so that the multiplication will be realized. So now, so you see V. So the V is wrong. So what is the problem? A times X minus L. So again, I must be careful. L transpose. Okay. So we now obtained our residuals. So let's now look at X. So as you recall, we must iterate several times so that we get the x values, the first three values, close to 0. So we can then understand, okay, this is the number of the iteration. So for this purpose, we need to make an iteration. Let's do iteration is equal to 1 to, let's say, 5, for example. 5 will be enough, and 4. So, and let's do the calculation. We will see the x is still 17 because we did not update our unknown. So we need to update our unknowns. How will we then do that? So we will do that by xyz 0 is equal to xyz 0 plus x 1 to 3. So, and you see x is a vector, so that's xyz 0 is again a vector, but it's a row vector, so that's why I must take the transpose of it. And now let's run again. So let's see x. X is so close, x1, x2, and x3. So the unit is meter. So it is okay. We are in the region that we can assume that the solution has already converged. So now here, let's have a look to the residuals. So the residuals are here. If you would like to compute our standard deviation, so here the standard deviation can be standard deviation can be computed by using the sqrt v transpose times v divided by simply the number of observations, so n minus number of unknowns. In our case, 3 coordinate unknowns and 1 clock unknowns. That's why. So it will be 4. So then let's have a look to our standard deviation. So you see 9.9 meters. So it's a little bit large because we have some problems here, and the problems can be understood. So So it can easily be understood by plotting, by using the azimuth and elevation here. Azimuth and elevation. So you can see the elevation. So for example, the 13th satellite is 1 and the 27th satellite will be 3. So this type of elevations is so small that the sinus will be distorted largely because it penetrates through the atmosphere and the signal arrives at the antenna, at the receiver, but it is distorted largely uh, compared to the other satellites. So for example, from the elevation of 9 degree or from the elevation of the 78 degree. So that's why these are the distances, the longer, having the longer distances. So let's have a look to the distances. For example, so 1 2 so the measurement. So this one, so p I, for example, 2. So let's have a look to the measurement. Sorry. So you see this 1.3 degrees elevation. So the distance from the satellite to the receiver 25.6 million. 25.6 million. So if you can look here, 3.4, 25.2 million. But on the other hand, if you look at a satellite having an elevation, or the maximum elevation values around 80 degrees, so it is 20.9 million. So the distance is larger. So that's why the atmospheric effect on these measurements, on these two measurements, are larger. So that's why let's for a moment exclude these observations. This is the 13th observation and the 27th to the satellite. So this means that the third observation from the beginning and the third observation again from the end. So let's exclude this observation and also the coordinates. Let's exclude the coordinates for the 27 and run again. So now the standard deviation, as you can see, we have obtained around 9 values, around 9. Now we obtained 4.7. So this is ideal, and by using this method you can achieve accuracies around 2 to 3 meters. So you cannot reduce the accuracy, so you cannot reduce to centimeter or decimeter or millimeter range. So it is impossible by using this methodology, but there exists some methodology called as precise point positioning, PPP, and it is based on the same processing, but it takes some extra other parameters, and it takes at least for the moment 15 to 20 minutes to converge to centimeter values, centimeter accuracy values. So now let's introduce another topic here. What about the accuracy in each component? So if we would like to obtain the accuracies in each component, we must multiply this standard deviation, standard deviation with the diagonal matrix. So my QXX matrix. So let's have a look, QXX matrix. So this is a 4x4 matrix. So this is the cofactor for the X component, Y component, and the Z component, and the fourth component is for the clock. So and by using the standard deviation times the diagonal of this matrix, so then I will obtain the error, okay, the accuracies in x, y, z and clock terms. So diagonal qxx, but I need to take the square root of this diagonal because standard deviation works, okay, with the square root of the variance. So now you see my, okay, x component in Earth-centered Earth fixed system or in Cartesian system around 4 meters. Y is again 4 meters, so 3.6 z in z component, and my satellite, okay, the receiver satellite introduces 3.2, okay, meters. So be aware, your receiver clock is accurate around 3.2 divided by the, okay, as you know, this is the multiplication c times dt, so the dt is around, so let's try to calculate the velocity of light is, so it is already introduced, c is 300 million meter per second. So let's have a look here. As you see, our satellite is so accurate that it has an accuracy around 1.1 times 10 to minus 8. So it's a huge accuracy. So so it's not so as good as the satellite's atomic clocks, but it's still good for the maintenance of a daily life. For example, if you would like to make a project containing containing that the traffic lights be synchronous in the entire city, so you can use this type of, okay, receivers, for getting this synchronization within the traffic lights. So another point here would be the DOP values, the so-called dilution of precision. So as you know here, I multiplied by the square root, okay, square root of the diagonal of my QXX matrix or my cofactor matrix for the unknowns. So the terms, if I take the trace of this cofactor matrix, okay, of the cofactor matrix diagonal elements, trace of the, okay, trace. So let's first get the trace of qxx and then take the square root. Trace means you sum, okay, the diagonal elements, okay, 0.78 plus 0.74 plus, and again, so the 4 terms will be added up. So now let's apply this. So this number, okay, this number is called as geometric dilution of precision. So if we include the first 3, so these x, y, and z components, we will then obtain, okay, so 1 to 3, 1 to 3, so sorry, so square root 1 to 3, so qxx 1 to 3, 1 to 3. So you see I am dealing only with this term, so I'm taking the, okay, so let's define with another matrix Q, let's say P, okay. Let's now take trace of this new matrix QP, okay. So now this number is called as position dilution of precision. The first one if we add up all the diagonal elements, all 4 elements, we obtain the geometric deletion of precision. But if we get the first 3 elements, x, y, and z components, diagonal elements, we get the position deletion of precision. So these numbers should not exceed the 3. So for example, what is the explanation for this? So if the satellites are distributed along the horizon, across the horizon, so you will get smaller values of this dilution of precision. But if you observe satellites, so for example, in a let's say not so distributed across the horizon, and if you observe, for example, in a street canyon in a city, so then you will get the trace a lower value. So let's try to apply this for this task. Let's eliminate the satellites having the values more than 60, more than 60. So, or the elevation angles correspond here for our case, so the 30, so the lower than 30 elevation angles will be eliminated. So let's try to do this in our example here. So these so let's have a look here. These are the these will be the satellites 5, 10, 15, 5, 10, 15. So 5, 10, 15. And so this is 13 is already excluded. That's why we cannot see here. And we 16 will stay, and 25. So we will exclude 25, 25, and 31. 31. As you see, 1, 2, 3, 4, 5 satellites are available. So we must do the same here at the observation site, so that there will be no problem handling the data. So 25 will be excluded, and 27 and 31. So now let's try to run. Let's try to run. So n. So what about whose? And p is so this p, as you can see. So we have some problems here. Let's do, because p will be problematic here, because it should begin with the value itself. So if it does not begin with the value, so we will have problem. So exclude. Now run. P is 10 by 2 here again. So we have n still 10, so it must not be 10. So the coordinates. I think we have some problem here. Let's close and open again our program. So let's run it, and we still have, so as you see here, the parse error. So the parse error 43, line 43. So parse error, line 43. That's why we are experiencing the problem.